Hello everybody, today we're going to do a projectile motion problem. So in this problem, you launch a foam ball from a homemade launcher at a friend who is 25 meters in front of you. Your launching angle is fixed at 38 degrees above the horizontal. Your friend must receive it in exactly 10 seconds after it is launched. What speed must you launch it with? All right. I'm going to go through and think about the important words in here. I know that my friend is 25 meters in front. I know my launching angle is 38 degrees above the horizontal, and that my friend must receive it exactly 10 seconds after it is launched. And then I'm looking for what speed would I need to launch it with. So I'm going to draw a picture, and I'm going to, in that picture, address all these points. I'm launching this object with a V naught. That's what I'm looking for, what speed. So it's the magnitude of the velocity vector of the initial launch. I know the angle is 38 degrees above the horizontal, so I draw my horizontal line and measure up 38 degrees. I know that the target is how far? 25 meters in front of me. So I need it to come back there, which means it's going to go up and down like that. Landing, launching. So this is my initial location. And this is my final location. And this happened at t equals 0. This has to be exactly 10 seconds later. So t final equals 10 seconds if I start my clock at 0 over here. If I'm starting my clock at 0, I might as well start my x position at 0 and my y position at 0. So that because it's horizontal all the way to the target, my y final would be 0 as well. And then if I started at x equals 0, 25 meters in front of me is going to put me at x equals 25 meters. Gravity points down. So a in the y direction is minus 9.8 meters per second squared. And I have no acceleration in the x direction because this is a projectile motion problem. So to solve all my projectile motion problems, I'm referencing my picture. And then I know that I have constant velocity in the x direction. Or you could think of this as the I hat direction if you're doing I hat, j hat. And I have constant acceleration in the y direction, which you can think of as the j hat direction if you're doing I hat, j hat. Constant velocity, there is only one equation for this. X final equals x initial plus v naught in the x direction, or vx, whatever you want to call this. It doesn't change throughout the whole motion, so it will remain the same. And then change in time. So with the givens I'm given and what I'm looking for, I can go ahead and plug in 25 meters for my final, 0 for my initial, plus now my velocity initial in the x direction. I don't have that. What I have is the initial velocity and the angle. So I'm going to write v naught cosine 38 degrees delta t. Oh, and my delta t I know. So I can put in Oh, you know what? I didn't want us to know delta t. I solved for delta t. Okay. Let's pretend we didn't have a delta t. We don't know. We don't know. And then your friend will receive it in exactly who knows after it's launched. Okay. Because if you have delta t, it would be trivial. You just solve this extraction motion and boom, you've got it. I was trying to show you a problem that required a little more effort. So when I did my solution, I plugged in the value I got, and then at least I'm sure I must have. Yeah. So let's pretend that we don't have it. Okay. So from here, if we don't know delta t and we don't know the initial velocity, we would have to stop. We've got like as far as we can get here. Then we go over to the y direction motion and work through it. Now, we're going to end up using equation 2 because we have positions in the y, we have initial velocity, we don't know final velocity. We could use that. I mean, there's always a million ways to solve these. If you're using symmetry, you could get away with using your final velocity here probably. But I'm not going to do that. I'm going to do the more basic solution and just say, okay, well, y final equals y initial plus v naught y delta t plus 1/2 ay delta t squared. So I'm using that quadratic version for constant acceleration and placed it in the y direction. My final is 0. My initial is 0. My v naught y is v naught sine, oh, I'm going to so run out of space here, 38 degrees delta t, and then plus 1/2 times negative 9.8, that's 9 minus 4.9 meters per second squared delta t squared. Oh, okay, I'm going to rewrite it a little further out here. So 0 equals, get rid of that one, just to make it look nicer, sine of 38 degrees delta t minus 4.9 meters per second squared delta t squared. All right. When you have an equation like this, you can factor out your delta t if you recall that from algebra. You can still use the quadratic formula. You would be plugging in 0 for your c in that. But this is easier. If we just factor it out, we're going to say we have a factor that looks like this, sine 38 degrees. I factor out a t. Like that. And when I've done that, if this equals 0, then I have two solutions. One where the first factor is 0 and one where the second factor is 0. So the second factor being 0 means that I have a solution where delta t equals 0. And that just tells me my object was at that point at time equals 0. Which it was. It comes back down to ground level at what time? Well, that's what this one is going to tell us when we set it equal to 0. Whoops, off the screen. Get back up here so you can see what I'm doing. That's what this one is going to tell us when we set it equal to 0. So that 0 equals v naught sine 38 degrees minus 4.9 meters per second squared delta t. V naught sine 38 degrees divided by 4.9 meters per second squared equals delta t. This, when I bring it over, it becomes negative. When I divide by a negative 4.9, then the negatives cancel so that I have a positive ratio over here. Now I can plug this delta t up here because this is the time when it was at the farther location, the range point, the 25 meters. it was at y equals 0 initially, time equals 0, and then it came back to y equals 0 later. And that later time is not this solution where delta t equals 0, but the solution where all of this equals 0. That's this one. So we plug that in over here, and we get 25 meters equals v naught cosine 38 degrees times all of that. V naught sine 38 degrees divided by 4.9 meters per second squared. So that I get 25 meters times 4.9 meters per second squared divided by cosine 38 degrees sine 38 degrees equals v naught squared. So that v naught equals the square root of all of that, which if I multiply that out, I get sorry, I just have to plug it in. There we go. Okay, so I get 252.05. And then units are meters times meters per second squared. So that's going to be meters squared per second squared, plus or minus over here because we take the square root. When we take the square root of that, we get 15.9 meters per second is my initial v naught. And you still have the plus or minus. You have to decide. V naught is a speed. It's the magnitude of the instantaneous velocity at launch. So the magnitude of a vector is always positive. So this is going to be the positive value. All right. Let's see. Oh my God. I'm using my cell phone as a calculator so I didn't have to run get my calculator. It keeps making all these noises. Sorry. Okay. So is there a way we can double check this? Sure. We can plug in our V naught and our time up in here somewhere and just double check it. So what was our time? If we were to actually plug in our time, we would have gotten 15.9 times sine of 38 degrees divided by 4.9. So that would be like 1.998. I'm going to keep lots of sig figs here for just a second. They aren't really significant, but just keeping them. So that would be our delta t for hitting the ground. So, oh my goodness. The amount of, here we go, there. The amount of noises that cell phones make. Okay, so if I want to plug that back up in here with my answer, I want to plug it in to this one and make sure I get 0 as a check. So, let's see, 15.9 was my velocity times sine of 38 degrees times time, which is now 1.998. So I'm saying I'm taking this one up here and I'm just going to rewrite it down here and fill in. So I got 0 equals v naught sine of 38 degrees delta t minus 4.9 meters per second squared delta t squared. So I'm plugging in my delta t and my v naught that I know. I'm just going to calculate it. So I've got that term. Then I need to add in 4.9 times my delta t squared, 1.998, square it. And I get negative 0.0023, blah, 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 blah. So this is a very small number, and within our actual sig figs, we round it, and we have 0. So what we expected to be 0 on the left-hand side, when we calculate this out with our values, we do get 0. So as you're doing your checks, always remember, you've got rounding involved here if you've been calculating all along. And so when you go back in and you double check your answer, it just needs to be really close. It's okay if it's not exactly 0. It would only be exactly 0 if you had like whole numbers or kept every single value. All right. So there we go. So I think we have concluded that we didn't make a mistake. Our units look good. I didn't confirm time here, but I can go right here and just say v would have been meters per second. Acceleration is meters per second squared. So did we actually have time here? Meters per second divided by meters per second squared. Yes, so that's going to end up being, remember, meters per second. If you're dividing it by meters a fraction, you just multiply by the inverse, so that we would be left with seconds. So that's good. Okay, well, I think we have done our best to make sure we got the right answer. And this is a good example of a problem where you don't know the velocity and you need to calculate it. And also a range problem, because you're doing the range for it to come back down to 0, to a height of 0. And that is it for today. So see you next time.